So we're asked to find an integral that represents the area of a circle of radius r and then evaluate that to get the area. So we're going to do this via slicing. So the first thing we want to do is we want to create a slice. Now the idea is that this slice is infinitely small, it has no height, but to be able to see it, we'll draw it as if it does, and we'll call that height dx, just to call it something. And now we want to call its other dimension something, and perhaps I'm only going to go halfway. I'm going to call this side the width of the ith slice. Therefore the whole length from here to here is 2 times w sub I, and this slice is a distance of x sub I away from my center. It's arbitrary, it could have gone up, could have gone down, could be right on that line. The sub i's mean they're just some arbitrary length. There's something that's going to vary depending on where we choose our slice. So we're going to start to build our integral by looking at the area of the ith slice. Well, it's a rectangle, so it's going to be from here to here, which is 2w sub I times our other dimension, which is dx. Now the problem is we have a couple variables floating around, so we'd like to get a relationship between w sub I and x sub I, because we'd like this all to be in terms of x. So what I'm going to do is I'm going to drop in a diagonal here, giving me a right triangle, and notice this side here goes from the edge of the circle to the center, so it has a length of r. So I have a Pythagorean relationship in that x squared plus w sub I squared equals r squared, which is why I chose w sub I to just be half of it. Could have let w sub I be the whole thing, and there's no problem with that, then you wouldn't have the 2 here. This would be w sub I over 2 the quantity squared. Still work out the same. We'll solve this for w sub I, so we get w sub I equals the square root of r squared minus x sub I squared. So putting that into my area formula, I got 2 times the square root of r squared minus x sub I squared dx. I've got those in terms of x now, so now I'm going to turn it into a definite integral. And because 2 is just going to be a constant, it doesn't depend on x, I'm going to pull it out front. And I've got in my integrand square root of r squared minus x squared, x being the variable, r is some constant. We'd be given the radius of the circle, for example, dx. The limits, well, this is going to go, here's the lowest possible slice, down when x is equal to negative r, and up here, the highest possible slice when it's equal to positive r. So there, in fact, is our definite integral. Now, to solve this definite integral, you could use the table of integrals, or we could use a trig sub. So let's go through it with a trig sub, and in fact we're going to let r equal r sine of theta, and therefore dx equals r cosine theta d theta. Alright, so let's plug everything in and see what happens. So we have negative r to r, square root of r squared minus, this whole thing here is going to get squared, so we're going to have r squared sine squared theta, because that whole term gets squared, times our dx, which is r cosine theta d theta. I see the dx get forgotten a lot on trig subs, so don't forget that part. Now, we have 2 times the integral from negative r to r. This is going to break down into the square root of r squared times 1 minus sine squared theta, r cosine theta d theta. And this is why we do the trig substitution, because 1 minus sine squared theta is equal to cosine squared theta. 2. And so now we're going to have something that's going to work out real nice with our square root. Because these are both squared and we're square rooting them, those are essentially going to cancel each other out. And I'm going to have an r and an r from there, so I'm going to pull those out front, so 2r squared, negative r to r, this will become cosine times that cosine, cosine squared theta d theta. So, to finish solving this thing, we have to be able to take the antiderivative of cosine squared theta. Tables of integrals is one way of doing that, but we also could do it using a trig identity. In fact, cosine squared theta is equal to 1/2 times 1 plus cosine of 2 theta d theta. Now that half will cancel out with that 2, and now we have something we can do the antiderivative of piece by piece. So we have r squared, antiderivative of 1 is theta, antiderivative of cosine of 2 theta is sine of 2 theta over 2, and these are going from negative. Oh, we should have probably switched our limits. Actually, let's switch our limits. Instead of using negative r and r, we'll use our relationship right here that we had between x and r. Now these were x values. If x is r, we get r equals r sine theta. And you can see if we divide both sides by r, we get sine of theta equals 1. So the upper limit, we could actually just use pi over 2. And with the lower limit, you'll see that we'll get a negative 1, so negative pi over 2. Now we don't have to switch back the thetas, and we can just do from negative pi over 2 to pi over 2. We probably should have switched our limits back up in this step up here, and I missed that. But you don't have to. If you go through here, you can get theta in terms of x, and then put in your original x limits. So we should be about done here. So we have the r squared out front, pi over 2 plus sine of 2 times pi over 2 over 2. So there's our upper limit, minus negative pi over 2 plus sine of 2 times negative pi over 2 over 2. And I'm kind of messy right now, but this is going to simplify real nice because 2 times pi over 2 is pi, sine of pi is 0, so this term is 0. Similarly, this term is going to be sine of negative pi, so it is also 0. And we got pi over 2 minus a negative pi over 2, or plus pi over 2. So pi over 2 plus pi over 2 is pi, and we get r squared times pi, or our very familiar pi r squared. So that's the definite integral and how we could solve it.